introduction. My presentation is based on our GSI paper, and the paper as shown here, reference as shown as a reference. And our method uses representation theory of Lie groups technically. I will not enter the details of representation theory, but I will try to tell the essence of our method, not only to experts of representation theory, but also to those who are not familiar with representation theory. Let's start. I will talk about first background and motivation, and we explain our method, which is introduced to attain our purpose in the paper as shown above. And our GSI paper is about the properties of G mod H method here. This is our method. And I will talk about future works finally. In the field of machine learning, learning by using a family of probability measure is one of important methods. Here, learning is mathematically to optimize the parameters in the family of probability measures. We often use exponential families. This is good class of families of probability measures. In fact, exponential families are important in the important subject in the field of information geometry, and are useful for Bayesian inference, and include many widely used families. These are examples of exponential families. Exponential families include normal distributions and Bernoulli distributions, gamma distributions, Wishart distributions, Mises distributions, and so on. Here is a definition of exponential family. We modify the classical, well-known definition of exponential family in the field of statistics for convenience to representation theory. Roughly speaking, exponential family is a family having this exponential form. By definition of exponential family, there are too many exponential families. Only a small part of them are widely used. Oops, it is too small to see. So let's enlarge here. There are good exponential families, like this picture. So we can expect there exist good exponential families. So we want a framework to understand good exponential families systematically. Here is a good observation to attain our purpose. Useful exponential families have the same symmetry as the sample spaces. Mathematically, sample space is homogeneous space G mod H, and the family on the space is invariant under the induced G action. Here G is the Lie group, and H is its closed subgroup. And writing a space by G mod H is a description focusing on symmetry of the space. Our method is a method to construct exponential families. This method generates many well-known exponential families, and families obtained by the method can be enumerated. Moreover, new distributions by our method are expected to be good. Now let's see the G-mod H method. G-mod H method is a method to construct a family of probability measures on G-mod H from a finite dimensional real representation of G and non-zero H-fixed vector. We will see the method precisely later, but roughly speaking, the procedure of our method is as follows. First, take Lie groups G and H and consider the homogeneous space G mod H. This is our sample space. Then we take finite dimensional real representation V and H fixed vector. Next, we consider the set of all relatively G-invariant measures on X. Next, we make measures parameterized by the direct of the dual of V and omega GH. Finally, we normalize them. Our method generates a good exponential family. In fact, by choosing these inputs, then we obtain these well-known distributions. To understand our G-mod H method, we consider the normal distributions later. We will see the detail of G-mod H method here, from here. In the left side, we show the procedure of G-mod H method in the representation theory, and the right side, we demonstrate how to generate normal distribution by G-mod H method. First, we prepare a sample space with symmetry. We take Lie group G and a closed subgroup of G and consider homogeneous space G mod H, denoted by X here. We will construct a family of probability measures on the homogeneous space X. In the normal distribution side, we consider a real line. Real line has a symmetry of scaling and translation. So the corresponding, we consider the corresponding semi-direct group G, and consider H like this, and consider the homogeneous space G mod H like this. Here, the first component of G represents the scaling, and the second component represents translation. Then we can identify G mod H with real line. We will construct these normal distributions with well-known form. Next step, in the representation side, we take 3 inputs, finite dimensional real vector space, and representation of G, and H-fixed vector V0. In the normal distribution side, we take these 3 inputs like this, respectively. Here, Sim2R is a set of symmetric matrices of size 2. Next, we consider measures compatible with symmetry. In the normal distribution side, measure is compatible with scaling and translation is essentially Rubeg measures. Mathematically, measure with compatible with the symmetry means relatively G-invariant measures. So we consider the set of all relatively G-invariant measures up to positive scalar. And we make measures with symmetry. In the representation theory side, we define measures parameterized by the dual, product of dual of V and omega GH, like as follows. Then, in the normal distribution side, we obtain this measure by taking an inner product naturally. Here, theta 1, theta 2, theta 3 are real numbers. Then finally we normalize the measures. Here we denote the parameters, such that the measure p theta is integrable. And we obtain a family of probability measures p theta by normalizing p theta tilde. Here, phi theta is the log normalizer. We can compute the parameter space large theta like this, and we can compute the log normalizer like this. Namely, we obtain the family of probability measures on R like this. By a change of variables like this, then we obtain a family of normal distributions with well-known form. The measures obtained by G-Monte's method has a good properties. Namely, the family obtained by our method is G-invariant exponential families. For example, in the normal distribution case, the proportion corresponds to the fact that a distribution transformed by scaling or translation from normal distribution is also normal distribution. Now let's consider the following two questions. Please recall families obtained by our method can be enumerated. To show this and enumerate practically, it is important to consider the following two questions mathematically. The first question is, find the following correspondence from parameter space to the distribution is injective. And the second question is, when do distinct representations generate the same family? We gave an answer to the first questions as in theorem 2.7, which correspond to theorem 1 in our GSI paper. We also gave necessary conditions, which is easier to check, like this, as in proposition 2.8, which correspond to proposition 1 in GSI paper. We do not enter the details of this proposition and theorem. Please read our paper if you are interested in. The next question, we gave an answer to the second question as in theorem 2.10. We define a natural equivalence class, equivalence relation. Then we show the equivalent elements generate the same family. Here is the definition of equivalence relation. In the rest of time, I will talk about future works. Our aim is to suggest new useful exponential families or probability useful families or probability measures on homogeneous space by Gmod 8 method. This is our message. If you want a good family of distributions on some spaces, please tell us the spaces. We will try to propose good families of distributions on them. We consider the following 3 examples for our future works: a sphere and upper half plane and hyperbolic space. There are famous distributions such as von Mises-Fisher distributions, Fisher-Bingham distributions, hyperbolic distributions. They were obtained heuristically, but by using our method, we obtain these distributions systematically. These examples is very important mathematically and practically. In particular, machine learning using hyperbolic space has been very active, so good exponential families on hyperbolic space has been desired. Now, let's see the first example, sphere. A sphere is defined like this, and the sphere has a symmetry of rotations. So we can describe the sphere as a homogeneous space like this. Then by considering low-dimensional representation, we obtain from these distributions and Fisher-Bingham distributions. By taking higher dimensional representation, we obtain families on sphere, which are not well known now, but was used in the paper Cohen and Wang. Next example is upper half plane. Upper half plane has also upper half plane with Poincare metric has a symmetry of actions preserving the Poincare metric. So we can describe upper half plane like this homogeneous space. Then by taking low-dimensional representation like this, finally we obtain the explicit distributions like this. By taking higher dimensional cases, we obtain new families by Gmod 8 method. This is a special case of hyperbolic space. The final example is hyperbolic space. Hyperbolic space has a symmetry of the actions similar to rotation for sphere. Then we can describe homogeneous space. We can describe the hyperbolic space as homogeneous spaces. By taking low-dimensional representation, we can obtain hyperbolic distributions. By using higher dimensional representation, we obtain new families. We want to apply the distributions to actual problems, by using higher dimensional representation, we can obtain better approximation. But the training costs become larger because parameter space become larger. So we need some techniques to optimize the parameter with low cost. These are references and messages. Thank you for your attention.